that one.
So we certainly will remember today. And I just started that. So again, thank you for the reminder. Let's see. Any questions you guys have about yesterday?
So one of the questions I had was on the first problem on the homework 9.1 on the critical value. Why does it come up negative? And are you always supposed to use the positive of that, or am I putting it in wrong?
Remember yesterday, let me actually bring up that thing from yesterday. Nice thing, you're not doing it wrong. Where's the one from yesterday? All right. Well, anyway, remember yesterday we started off with that chart?
Yes.
And we found the these scores associated with,
yeah.
And when we did that, we find those two z-scores, the -1 and the +1, right?
Right.
The critical value is essentially the absolute value of that.
Okay.
It's how far out are you going? Because remember, in our little formula, we end up adding and subtracting it.
Okay.
So the critical value is always just the positive version.
Okay.
But generally, the first one we find with because we're using the tails, the first one we find is that -1 in general.
Oh, yeah.
So it always feels like it's kind of like, why is it using the -1?
Okay. And then, could you clarify, like on number 9, it's just that understanding those phrases and why, which ones work and which ones don't.
Well, let's take a look at it.
Yeah. Somebody needs to respell proportion.
Needs to what?
The first one, in all the questions like this one, they missed proportion.
Yeah, I would never notice that.
Oh. Spelling bugs me.
Be like, oh, I must drive you nuts then. While we're looking at that, why don't we look at
and that one too, yeah,
as well.
Yes.
Okay. Actually, let's start with that one just because it's short. This is essentially asking you which calculator command, if you want to do this straight with a kind of a one tool calculator, which we're not really doing. We're essentially doing though you could, we're taking that sample proportion, adding the z-score associated to our critical value and subtracting it, multiplying that by our standard error.
Right.
But the calculator does have a tool where you can just kind of throw in all of that information. And it is one proportion z interval.
Okay.
Fair?
Yeah.
So that's the distribution tool on your calculator that you could use to do this kind of all at once if you really wanted to. And your book talks about that tool. Was that Ken?
Is that under VARs? I mean, under distribution?
I would think it's under distribution, but I don't ever use it. I do it by hand, so I don't actually know where that one is. But I think it comes up in your textbook.
Okay. Does it tell us where it's at? Because I'm not seeing it on my calculator.
Look it up. Let's see. Oh, that doesn't tell me where it is. Let me type that. Test. Stat test.
Yes. Yep. There it is. Okay. Thank you.
Sure. Okay.
Okay.
Excuse me. So that Camille, you asked that. Does that make sense?
Asked what?
This question about the one prop Z interval.
You said it's something that is used for the calculator, and it's on my calculator, but I didn't find it.
Yeah, it's under the stat tests, but we don't use it. So it's almost just like textbook
Okay.
textbook question. It talks about using it if you want to. You certainly can if you want to, but that's what that means.
Well, it'd be a nice check, you know.
Yeah.
Nice to be able to check it. Right.
But Kim, your question about the vocabulary is nice. So let's look at that. I see a student was asked to find the 98% confidence interval for the proportion of students who take notes using data from a random sample of size 86. Which of the following is a correct interpretation of the interval of a proportion between 0.11 and 0.25? So I'm going to draw a picture because, you know, I draw pictures, right? So they found some p hat. That p hat is presumably in between the 0.11 and the 0.25. And they have an interval from 0.11 to 0.25 that they think the mean should be in that interval somewhere. So the mean of the sampling distribution, which is the true proportion, should be in there. Yeah, this interval. Is it necessarily in that interval? I'll say no, it's not necessarily in that interval. How confident are they that it's in that interval? 98%.
98%.
You're 98% confident that the true proportion is somewhere in that interval. So let's look at these statements and see which one of these kind of line up with that. The proportion of all students who take notes is between that and that 98% of the time. Is that what the 98% is saying?
No.
No, they're saying that the true proportion is somewhere in between. We're 98% sure the true proportion is somewhere between the 11% and 25%. We're making no argument about how often it occurs within that range. So that's, sounds kind of close, but not what our confidence interval actually says. There's a 98% chance that the proportion of the population, it's the true proportion of the population, is between 0.11 and 0.25. Is that what our confidence interval says?
Yeah.
Yeah, that's a good one. There's a 98% chance that it's in that range, that the true proportions in that range. Let's see. There's a 98% chance that the proportion of note takers in a sample of 86 students was between, or will be between 0.11 and 0.25. That one's a little more complicated.
Yeah.
So there's a 98% chance that a proportion of note takers in a sample of 86 students. Well, if we looked at our sampling distribution, right?
Mm-hmm.
Our sampling distribution would have its true proportion. Fair? And if we made a 98% confidence interval around that true proportion, then that would have certainly a low and a high, right?
Mm-hmm.
And there would be a 98% chance that any particular sample would land in that range. And that range would be the same width as this range, but the centers are different. This range, how long is that range? 0.14 is how long that is, right?
Mm-hmm.
So this range around the true proportion would still be 0.14, but its high and its low actual value would be different because it's centered around the true proportion as opposed to being centered around the sample proportion. So this one is very close, but not quite.
Okay.
Fair? Our confidence intervals tell us about where the population value is, not about where the samples are.
Okay.
So that one is almost true, but not quite true. Let's see, with 98% confidence, a randomly selected student takes notes in a proportion of their classes that is between 11 and 25%. How do you feel about that one?
I think that sounds okay.
No, because it's talking about the proportion of classes.
Yeah, in proportion of their classes.
Yeah.
Is this about proportion of classes?
No. Population.
This is about a proportion of students, right?
Proportion
And
of
this
students.
switch to talking about an individual student and a proportion of classes as opposed to a class and a proportion of students. Fair?
Okay.
With 98% confidence, the proportion of all students who take notes is between 0.11 and 0.25.
No.
Why not? Or why not?
Because it's telling you that that's exactly what's happening, and well, I don't know. I thought of something else, but maybe I'm wrong. Because it's still talking, I don't know. Dang it.
So it's just a difference between proportion of the population and proportion of all students.
Yeah, it's because it says all students. Proportion. I don't, I don't know.
Well, and that kind of depends on what is the population of this event here. A student asked to find a confidence interval for the proportion of students who take notes. So saying the proportion of the population, well, what's the population? Population is students, right? So those are essentially the same statement.
Okay. Okay.
All students is the population. So these are just two different ways of wording that. So those are essentially the same statement. Probably the most common kind of misinterpretation are ones like this second one or this first one. Like 98% of students will take notes in between 11% of the time and 25% of the time. That kind of misinterpretation. That 98% is not a 98% of students, it is a 98% of the, how do I want to say that? Without just restating that it's a confidence interval. Yeah. It's the span over which we think that true proportion should lie. Fair. Anything else from that homework?
One other thing, could you just, I know we're not going to use the one prop Z integer on the calculator, but if we wanted to check our answers that we've done using that as a double check, could you help? I don't know, like, could you look, like, can we do number 8? Can we get the confidence levels with that?
Well, let me see. Prop Z interval. It's interval, not integer.
Prop Z, oh, not test. Oh, interval. That's what I was doing wrong. Okay. And then mine says X1, N1, X2, N2. And so, and then
what's the
confidence level, you can just enter, I'm assuming. It goes to 95, but if you want something other than 95, you could do it.
right?
So what are, like, say we did problem 8 on the calculator.
Let me pull something up real quick here.
Or yeah, one of those problems.
You're just not gonna let me not look at the calculator. I know you guys like the calculator. So, and then you wanted to look at number 8.
Yeah, let's do that. Because I'm struggling, like, there's so much of a process here. I didn't even know, like, I totally didn't hear apparently anything about your p hat. And then when we tried to use your
Critical error or standard deviation.
is that what it was that we messed up on?
Yeah, it goes p hat, which is the proportion of how many you have out of the total. That's
The
your
sample proportion.
I mean, yeah.
there is a lot going on in these.
Yeah, and just,
So out of the 600 sampled people, so that's immediately our N, right? 438 prefer the candidate. So out of that, there are 438 that prefer some sort of candidate. So if we were looking for a proportion of that sample, what proportion of the sample preferred that candidate? Well, 438 out of the 600 sampled. Okay. So we could get that proportion if we wanted it. Based on this, estimate the proportion. I'm going to first do this like we had been doing it.
Okay.
Fair? Based on this, estimate the proportion of voters of the entire population, so that's our confidence interval, that prefer candidate A, and we've been told specifically to use a 90% confidence level. Okay, why not? So what is this proportion, just so we've got that value? 438. Go ahead.
0.73. I only got 2 numbers. I know you want it rounded to 4, but
I'll take the 2.
no, it works with 0.73 because that's what I got too.
Well, it might actually just be 0.73, and that's just, there is no.
Yeah,
Okay.
yeah.
So 0.73 is 00 if you want.
Don't do that.
What's that? Don't do that?
Don't add numbers. Don't play games.
They're always there.
No.
Okay, so we know that our p hat is going to form the center of our interval. So we know it's going to be around that 0.73, some distance up and down, centered at that 0.73. We want to figure out how far up and down are we supposed to go. That's our margin of error on both sides. Well, how do we find that margin of error? That's our critical value, our Z for the 0.05. Again, that 0.05 is the tail size for a 90%. Times our standard error. How do we find standard error? That's our square root of PQ over N. As we talked about yesterday, we would like to use the P and Q from the actual population, but we don't have them, so we're going to use the sample P or the sample proportion instead because it's the best we got and it's usually close enough. So our sample proportion was the 0.73. Our critical value for a 90% was, what was that, the 1.65?
1.64?
1.64, okay. And then that's square root of 0.73 times 0.27 divided by 600 for standard error. Now, if we want to put that in all at once to maintain accuracy, that can be really helpful, but it's not the easiest thing to type into your calculator all at once, but it's good to practice.
Yeah, it's not. I was going to ask that. Because I tried and it gave me crazy numbers. So I was having to like break it down.
And that's not at all unusual or unreasonable. It is a lot to put in all at once. So if you want to find that standard error separately, that can be really handy. So RZ for our 0.05 is our 1.64. You found P hat at 0.73 and calculating that standard error. Anybody want to give us a value for that standard error all by itself?
0.0181. That's just for that little part with the square root of 0.73 times 0.27 divided by 600?
That's the standard error.
That's that. Okay, yeah, it's 0.0181.
If you wanted to do it in pieces, that product would give us the margin of error. We were doing that a lot yesterday because I was trying to make sure you guys got that idea of what the difference between the standard error and the margin of error was. So what's that product between the 1.64 and the 0.0181? What is that margin of error?
0.0005. 0005.
That seems awfully small.
I got 0.0297.
Oh, it's because I forgot the square root again.
Yeah, that's what I got too.
Ah,
Well, and again, keep in mind, this is our plus or minus. These are both essentially percentages. So at 600 people, being almost a plus or minus of 3% is very reasonable.
Zero two nine seven is what you guys got?
0.297.
Oh, I wrote down. I got 0.295. I guess.
Oh, and that just be rounding.
Yeah.
So if we were posting this on a candidate site, you'd probably say something like 73%, and then put that little plus or minus 3%. That would be a perfectly normal looking thing to write. They want accurate to 3 decimal places. So, and they want it as an interval, right?
yeah. That's right.
What proportion of the world population? We could do it either way, but
Okay.
you would get what, 0.7597, so 60 if you round it up on the high end, and on the low end you get what, 0.701.
Yes.
I got 0.700 and 0.760.
Okay, 700, I believe. I'm just trying to do it in my head. Yeah, it's a headache.
Yep.
So between 70 and 76.
Yeah.
Questions about, before we look at, trying to see if what the calculator says, questions about that process. There's a lot to it, but the nice thing is you're used to finding standard error. So, kind of finding these pieces, we're kind of used to finding these pieces, even this from chapter 7. Once we have those pieces, putting it together into our confidence interval is just taking those pieces and pushing them together.
Okay.
Now, you said you wanted to use the calculator for it. The calculator takes in the, again, this is under the, you go to your stat menu, then to tests, and there should be one prop z interval, because this is a proportion. It's a proportion under one variable, and we're using z-scores to find an interval. So one proportion z interval. And it takes in 3 arguments. It takes in x, n, and what do they use? Do they use p? Doesn't matter what they use. I'm going to use C for confidence level. So that X is the amount of positive counts, N is the sample count, and C is the confidence level. So in some ways, this question, which is number 8, is almost set up perfectly for this, because we're told the 438 of the 600, and we want 90%. So it's kind of given to us in that form, which I suppose is nice, and probably something they did on purpose. So if you put that one prop Z interval 438, 600, and 0.9 or 90%, what does it now? Does it want the 90, or does it want 0.9, or does it want 90? Do you know? I don't know. I would do the 0.90, but that's because
It just changed it. I put 0.90 and it just changed it to a 0.9. And so it gives me 0.700 and 0.7598. So yeah, 0.76.
and 0.758.
It's 0.7598. So it's
98.
0.76. Yeah.
Oh,
So
yeah.
to 3 decimals, 7.6. Okay,
Right.
so it works fine.
Yeah. Okay.
But you know how I am with knowing what you're doing.
Right.
But perfectly fine tool.
Thanks, Matt. Thanks, Matt. I gave up my math career again yesterday.
It happens from time to time. History major starts to look good every once in a while, but it's really not the best life. Okay, anything else from those? Are those giving you guys a big problem, or is it just kind of getting used to it and needing some of that practice? Or Andrew's just like, yes.
I was struggling, but we'll just see how today goes. I think it's because it's just like you're telling us the whole thing and all of the new words with it. Like it takes me a second to process that. And like I had a little bit more time to understand the binomial and all that stuff, and then get the vocabulary down. And then now it's like, so.
Yeah, from a mechanics perspective, we're really not doing anything that dramatic.
No.
But it is
No.
a different way of talking about it, a different way of looking at it. Yeah, so it is
Yeah.
It's certainly a thing.
Yeah.
So let's just say, given a sample of, let's say 100 parts that you're manufacturing these parts, you have let's say 1.2%. Not bad considering what you're making, depending on what you're making. Can we 95% confidence? Why did I have an I? Oh, interval. Confidence interval. True proportion of failing parts. So we make parts. We make hundreds of thousands of parts out of this factory. We have a failure rate of 1.2%. So as they're coming off the assembly line, a person takes each part and hooks them up to this electrode thing, and that electrode thing either has a green light that says it works, or a red light that says nope. If it's a green light, it goes down the line. If it's a red light, it goes in the bin to go and be fixed, right? And we have a sample of 100 of those, and out of the 100, 1.2% of them fail. So it's not too many, but it's you know, something we want to know. But that doesn't mean the entire factory run fails at 1.2%. It should be around that. But if we want to turn this into an inferential statistic, so we can have a solid argument about our overall population of parts, what our overall fail rate is, partly so we can make arguments about, you know, what would be unusual, bring some of that standard deviation arguments in there. We'd want to have a range for where that true proportion is. So given this information, can we find a 95% confidence interval for the true proportion of failing parts?
Our number is 100 parts. Confidence is 0.95. Number 100, and the fail rate is our X. Can we find a 95?
Now let me stop you.
No.
What does this question ask?
Get a sample one.
Or how about this? What is the answer to this question?
It's asking about a sample. Given a sample.
It asks, can we find a 95% confidence interval for the true proportion? The answer to that question is either yes, no, or I don't know.
Oh.
Right?
Right.
So unless your answer is yes, no, or I don't know. So how do we determine if we can even do this?
Mhm.
Isabella, were you talking to me or are you talking to something else? Something else is fine.
I think I'm just trying to like piece it together in my head. I might be directing it at you, kind of at myself as well.
That's great. That's perfectly fine. I just wanted to make sure you weren't hearing, or I wasn't supposed to be hearing.
Yeah, I mean, you could have heard me, but it might have just sounded like delusion.
So how do we determine if this is even possible to answer?
Is it greater than 10?
Is what greater than 10? But yes.
Is
Sample size?
or the population greater than 10?
We don't know anything about the population other than the fact that it's hundreds of thousands.
Is PQN greater than 10?
I usually use NPQ, but either way, is that product bigger than 10?
Right.
So is 100 times 0.12 times 0.988? Well, I got to put that in proportion. 0.012 times 0.988. What is that product equal to?
$1.1856.
Is it bigger than 10?
Nope.
So what's the answer this
No.
question?
Nope.
The answer to this question is no. Because our sample size isn't large enough for us to have a normally distributed sampling distribution. And I mentioned that's usually that hasn't been an issue, right?
Right.
What about this problem made it an issue? Sample size of 100 is not crazy small. What about this question is a little on the extreme side and made this an issue?
The percentage parts.
I said when these percents are fairly extreme, you got to be careful, right? So if we did want to find a 95% confidence interval for the true proportion, what would we need to change?
To change the population size.
Well, population size, you're close though, right idea.
The number,
The
Like,
sample size.
the sample size has to be larger.
So let's say instead you grabbed 1,000.
Yeah.
Is that big enough?
Yes, because then it'd be 11.
Right.
Point. Yeah.
Then it would be 11.
Yeah.
Okay, so that's gonna change us to a yes. And that's always something to be careful of. If you're like, doing a test and it says, can we find a 95% confidence interval, and you give the confidence interval, you were asked a yes or no question.
Mhm.
So, yeah. But, we're going to say, okay, then find it. But this is an easy step to forget. You guys kind of forgot it yesterday, and so it's kind of forgot it a little bit today too. So.
Yeah.
I
Yeah.
gotta keep throwing it at you until you're all like, oh yeah, the NPQ thing.
We did have to answer that in number 1.
Mm-hmm.
And number 2, I mean, they say state the parameter and verify the necessary conditions. So that's kind of what we did there, right?
Yep.
Okay.
And again, we have most of the information. We have our sample proportion, 0.012. The z-score for a 95% is known to us. If we didn't use 95%, if it was some weird one, we could go find it like we did at the beginning yesterday. But 95% is our 1.96, or almost 2. The only thing we actually have to do on any kind of scale is find that standard error, right? That's usually the big job. So that's standard error, the square root of our p hat, because that's all we have, times our q hat, 0.988 divided by that 1,000. And then don't forget to find that square root, because we seem to like forgetting to find that square root. It's easy to forget. And again, you can put it all in one formula, but break it down so we can see our parts. So what is that standard error about?
0.0034.
0.034, which is fairly small for a standard error, but our sample size is 1,000, so it should be pretty small. Again, to remind you, just in case anybody ever asks you what the margin of error is, there's a hint there. I will tend to ask you what margins of error are. But it should be somewhere around 0.00, is it 6.7 or something?
Yeah.
6.7, okay. And then 0.012. So depending on how we want to round, let's say we're rounding to 3 decimals. So that would be a 1.2% plus or minus 0.7% if we wanted to round our proportions to 3 decimals. And if you wanted to write it as an interval, you could go, what, 1.9% on the high end. I know I usually don't write them as percentages, but it's good for me to be flexible sometimes, right? So from 0.5% to almost 2%. I'm going to give you options until you tell me not to anymore.
So just out of curiosity,
Mhm.
I follow that. If you want to test that with the calculator, what is your X and your N? Is your N 1,000
Yep.
and your X is 1.2 times 1,000? No.
Yep. Well, 0.012 times 1,000.
Yeah, 0.012 times 1,000.
So
Okay.
if out of 1,000 parts you had a 1.2% failure rate, that means it failed 12 times.
Right. Okay.
So that X is your 12. So this problem, unlike that question 8 that we looked at, that you were
Right.
essentially given the information in the proper form, here you're not given that information in that form, so you've got to figure it if you want to use that tool.
Cool, and it worked.
Good.
Well, except
It
No,
rounded a
yeah.
little bit differently.
oh no, I see. It came out. No, that's right.
Mhm.
And
Make me nervous, Kim.
I know. No, it just came out as a decimal instead of as a percent.
Like those.
The answers. Yeah, like those. Yeah, absolutely. Okay. Now I'm paying attention. Thanks.
Okay. let's look at one more of those, and then we'll start talking about our continuous, which we'll talk a bunch more about tomorrow. Let's say what sample size do you need to ensure a margin of error of less than, let's say 2% in a, let's do that, 99% confidence interval. I'm actually going to give you a couple minutes to play with that. It does have kind of a mean twist in it, not twist, but a mean piece to it that we talked about yesterday. So we'll see how that goes.
Okay, let's.
So I'll give you a couple minutes.
Oh, no.
Okay, so I'm just guessing here, but Matt, would it work if you just took the formula for the confidence interval and used 0.02 as your, what's the first one? Critical value? No, what's the first one? I always forget.
Oh, the sample proportion?
No, aren't we looking for the number that's on the bottom of the square root?
The n, the sample size? Yes.
Yeah. We're looking for that, right? So we're just working.
But it's less than 2%, so it would be 0.1, right? Or no?
No.
No.
Oh, JK.
Because less than 2%, 1.999999 is less than 2%.
Right.
So
Right.
it's not discrete, so we can't do that. What is that 2% supposed to be equal to?
It's I know. It's not quite yet. It's,
When we're talking about the margin of error, has to be less than 2%.
Yeah, that 2% is a margin of error. So
Okay.
like, it's not our P. We don't have a P.
right.
Yeah.
It's not our Q. We don't have a Q. We don't know either of those. The standard error is the square root of P, which we don't know, Q, which we don't know, over N, which we don't know.
Right.
Well, the only thing we would know is the critical value because of the 99%.
Good. What's the Z-score for that 99%?
0.58.
19.
It's 2.5.
2.5 what?
8.
2.58. So we know that.
N
Yeah.
equals 1.77.
How do we find margin of error?
What are you doing? I don't know what you're doing over here.
Standard error times critical value.
So the margin of error is this product. So we're not asked for P hat, right?
No.
So P hat, you know, we really, this whole P hat plus or minus, we're not asked about the P hat. We're asked to make that margin of error. That margin of error should be the Z-score multiplied by the standard error. So it should be the 2.58 multiplied by that square root of P times Q, which, as you guys said, we don't know,
Right.
over the N. I'm gonna leave that blank for a second. But what's this supposed to equal?
What?
0.02.
0.02.
Why can't?
And you're right, we want less than, so as long as the sample size is larger than what would make 0.02, this error is going to be less.
So, we can't do 0.99 times 0.01
No.
and 258 divided by 0.02 equals 1.277? That's all right? That's not how we find that?
Why are we multiplying 0.99 times 0.01?
I don't know.
I feel like you're kind of trying to push together your numbers, you know? That's common when we're not sure what to do. I'm in a word problem. So that less than is a little bit of a, not a trick, but it's a little bit, often makes us overthink this problem. If we figure out the sample size that makes us have a 2% error, then any larger sample size will make us less. So we're solving for that 0.02, even though we want it to be less, just make sure our sample size is anything larger. So we don't have to do anything with that less than. Just that 2% is going to be our goal. That 99%, is what generates our critical value. So that 2.58 is what that 99% is doing. Fair? We need to multiply that by a standard error. The problem with finding the standard error is, one, we don't know the N, but that's okay because we're trying to solve for N, but we don't have a P and Q. What are we going to use for that P and Q to allow us to do this problem?
Oh, you. I don't know. You said it yesterday. Some.
Just use the letters P and Q.
Well, then we'd solve for n in terms of P and Q and still not have an answer. You know, what sample sizes do we need? You'd tell somebody, well, we need this much multiplied by the proportions. So, well, we don't know the proportions. So what sample size do we need? I don't know. What's the proportions? Well, to find the proportions, you need to do the sample. Well, how big should the sample be? We still don't know. Now, yesterday we talked about doing a preliminary sample to get an estimation, right? But what did we say we do if we don't have that? Are you remembering we talked about it?
50-50.
Assume that's a 50% chance.
You make it the worst case scenario,
Which
Which
is
is-
100?
50-50.
Oh, 50-50.
Oh.
What's the hardest type of, like, if you're trying to get a sense of an election and you want to make sure that you're picking who or predicting who wins and who loses as accurately as possible, what's the hardest election to call? An election where one person is getting, say, 80% of the vote and the other person's getting 20% of the vote? Or an election where the vote is 50-50 right down the line?
Yeah.
If it's 50-50 right down the line, you need to make sure you get a lot of information to call which side of that line it's going to fall on, right? That seem reasonable? So that 50-50 requires the largest possible sample size. Now, chances are it's going to be bigger than we need, but we need to ensure that the margin of error is less than that 2%. And with no other information, we have to go worst case scenario. So if you don't have a P and a Q, use 50-50.
So then I got 4,160.
Oh, that doesn't seem unreasonable.
No.
1, 2.
That should, you know, why'd you change it to Matt? That second, shouldn't that still be 0.25 there?
Because I took it square root.
Oh, okay, you took it out of the square root. Okay,
The square root of 0.25.
Right. okay. Yep.
I don't
just
have a
did-
calculator. I can't do all your fancy stuff.
Okay, I squared both sides. I divided then squared both sides.
Not unreasonable. Again, I just don't have a calculator, so I got to move the symbols.
Right.
And I like to show you guys that you can just move everything around,
Right.
depending on how your algebra is.
Yeah.
So Kim, you said you got about 4,000 and change?
1,160. 0.25.
Anybody want to back that up? No.
Yeah, that's what I got too.
Yay!
Did you get that, Kim?
You didn't get that?
I don't know. I didn't.
Okay, just be careful of those parentheses. So you have to have, it's entering on that calculator, I think that's giving you trouble, Camille.
Yeah.
You have to have double parentheses to do this last step. So
Yeah.
times
Point.
0.5.
I don't think I'm entering it in right.
divided by 0.02, and then all of that. Oh yeah, you can enter it like that. Okay. Yeah.
Oh, that is not what I'm doing.
That assumes you solved it in that particular pattern,
Yes.
you know, which would
Right.
probably be a slightly weird pattern to have solved it by hand or
Right.
with the calculator.
Mhm. I always put, Matt,
Mhm.
I'm used to it. It's multiplication, but before division from left to right. So you really don't have to. I always err on the side of putting another set of parentheses around the multiplication over the denominator.
Which is not unreasonable.
Right, but
It would be necessary in the denominator.
yeah.
So let's say we were going to walk through it and we had a calculator and wanted to do it that way, just to make it, you know, what would you do? The first thing you'd probably do is divide the 0.58 or,
Right.
or 2.58.
Yeah.
And what is the 0.02 divided by 2.58? .0078
.0078.
equals that square root of 0.25 divided by n. Then you'd square both sides, right?
Yeah, that's how I did it. That gives you 0.00006. 0.4 zeros and a 6 equals 0.25 n.
And
Multiply both sides by n and divide by 0.000.
so then n divided by that stuff, divided by that stuff. So 0.25 divided
Yeah.
by 0.00006.
Yep.
And you get about 4,000.
Yeah.
Now, chances are, if you were doing a study, 4,000 would actually work because, again, 50/50 is our worst case scenario. But if you want to ensure that the margin of error was less than 2%, you'd need at least 4,161.
Yeah.
In your sample. But again, chances are 4,000 would be sufficient.
Yeah. When I did it too, I didn't round. I used the actual answer for the
Yeah.
0.40. And so that's why mine is 4160. But if you do this right here, what you have,
Mhm.
it's 4167.
Okay.
That just makes that little bit of difference.
Ish. Yeah.
Yeah.
Well, you know, and that's why I do this, just because then I'm not approximating anything. So that tends to be one of the more difficult questions because it feels like you have no information. And because you don't know what your p hat is, you don't even know what your p and q might be. So you have to kind of do something that feels like you're kind of making them up, and that kind of feels weird sometimes. And you're making them up as if they're worse than they could be. So I think that's a good question to practice, and something that I don't think your text does enough. And also something that the calculator is not good at. I mean, there's no, like, you know, what's the one button I can push to make the calculator do it? There isn't one. It's a solving. Questions about that before we start looking at 9.2? You guys want to start looking at 9.2, or do you want to keep working, you guys want the kind of mental space to stay with this 9.1 stuff and then talk about 9.2 tomorrow, or do you want a little introduction to it? What would be good for you guys? I don't want to overwhelm you. Some of you look overwhelmed. Some of you look like black squares with names on them. Rory is still giving me that emotionless stare that he always gives me. It's very intimidating, Rory. Just teasing. Opinions, thoughts?
I'm struggling. That's where I'm at.
Would you be best to wait for 9.2, or do you want to hear some of that so you can have that gel until tomorrow? You're like, I got nothing. I don't know. That's fair too.
I kind of want to say stick to 9.1, but also I'm trying to learn 2 chapters at the same time because I have to get stuff done next week.
Yeah.
Yeah,
So,
Michelle
Well-
is trying to work ahead too,
Yeah.
and so it might be nice to have it in the recording.
Okay,
9.
well, let's just give a nice introduction to it. So let's say instead of this being a problem on proportions, let's say it was a problem on means. So you find, again, it's going to sound very similar. You find a sample of 100 people and determine their average, mean average, of course, their average something. I need something about that. Let's go grade point average because we're a school and we all care about grade point average, right? And you find their average grade point average, it's a weird statement. Their average GPA is, oh, let's say 2.71. Find a 95% confidence interval for the true average of all students in the population, so all students. Excuse me. So ideally, this should seem very similar. It would seem reasonable for us to say, okay, we don't have, before it was our sample proportion plus or minus the z-score times our standard error, the z-score for whatever critical value we were at. That was for proportions. For means, it might seem reasonable to take that 2.7, that 2.71 is our point estimate, and we know it's going to be around that 2.7. So again, we're trying to figure out how much margin of error we have, and the bigger our sample size, the better that margin of error is going to be, and so on. Fair? So we're still, and we're going to do that. We're still going to take our X bar, our average, our sample average, sample mean in this case, and add and subtract a margin of error. Just like before, we're going to take that sample mean, add and subtract a critical value. I'm just going to put critical value, multiplied by standard error. One of the big differences is in that standard error is no longer going to be that square root of p q over n, because this isn't a proportion problem, right? Mm-hmm. Because this isn't a proportion problem, it's a distribution of means. What is the standard error for a proportion of means? Or for a distribution of means, sorry. What was our other formula for standard error?
Standard deviation.
Divided by
Square root of n.
square root of that sample size, right? Now here's the problem. Just like in our proportions, when we had that standard error, it was the square root of p q over n. This p and q is the population proportion, not our sample proportion. But for proportions, it's close enough. Using the sample value instead of the true value to find our standard error doesn't bring in a lot of variation. So it's good enough, works very well. Using a sample standard deviation to approximate the population standard deviation brings in too much error. But it'll be the only thing we have. We don't know what the population standard deviation is. We are going to have to go find a sample standard deviation. So we'll have to have this average of 2.71 with a standard deviation, say, of 0.2. So because we won't have this value, we have to use S instead, and that brings in an unacceptable amount of error. So how do we compensate for that error? We compensate for that error by not using z-scores. What we use instead are what's called t-scores. Instead. Now, what's the difference between a z-score and a t-score? Very little, frankly. Our z-score says for a normally distributed curve, has some average, and the z-score is how many standard deviations we are away, right? What a t-distribution is, what a t-score is instead of it being this normal bell-shaped curve, it's a curve that's the same basic shape, but it's a little bit flatter and a little bit wider. So if in the black curve, if this, space between Z1 and Z-1 held 68%, that same 68% for the t-scores is just a little bit wider. It gives a little bit more room for error. Fair? Now, how much does it widen it out? Well, how much it widens it out depends on our sample size. The larger the sample size, the closer we can get to a normal distribution. So if your sample size is really large, the t-distribution ends up looking a lot like the normal distribution. If your sample size is small, it ends up being really wide, giving you a lot of space. So what does that look like in practice? Well, in practice, what we have is, instead of z-scores, we have t-scores. And I want to look at some of these t-scores before I let you go. So let's say we were trying to make a 95% confidence interval. So that problem, we want a 95% confidence interval. So a 95% confidence interval had a z-score of 1.96, right? What's its t-score? Well, one tail at a 95%, our one tail is 0.025. So this column is our 95% confidence interval. I think this particular table even has at the bottom, yeah, 95% down there. And it gives us t-score values depending on our sample size. So if we go down to the bottom of this column, let's start at the bottom, way at the bottom, if we have a very large sample size 1,000, it's really close to that 1.96 that we like. It's a little bit bigger, but not much. If we said the sample size was approaching infinity, it just becomes that z-score of 1.96. But notice the smaller the sample size, the larger the t-score becomes, giving us more space to account for, one, the small sample size, and two, to account for using standard or using the sample standard deviation instead of the population standard deviation. So it corrects for our error. So our sample size of 100, means the t-score we should be using at 100 is that 1.984. So it's a little bit larger than the z-score, again, to account for our error. So we would be taking that 2.71, adding and subtracting. The t-score, which was 1.98, was it 982? 984. 984. And then we can use our sample standard deviation because we paid the price for it by using the t-score, dividing by the square root of our sample size, and have a nice confidence interval. So when we talk about doing confidence intervals for means, the only real difference is this issue of having to use t-scores instead of z-scores. Again, what do the t-scores do? They allow more room because of the error of using the sample standard deviation. The only time we don't have to use t-scores when doing confidence intervals for means is if we actually have the population standard deviation. If, for some reason, somebody knew the population standard deviation in this problem, then you could use that population standard deviation and use the 1.96.
And that 0.2, you're saying if they gave you the standard deviation.
Well, we went and found a sample, right? So from the sample we find the mean and the standard deviation. We have to have both of them.
You have to have both of those.
Right.
Okay. Okay.
But you generally won't have the population mean because that's what you're trying to approximate. And if you don't have the population mean, the chances of having the population standard deviation are really low. So generally, we don't know either of those. And to compensate for the error that brings in, we use the slightly wider t-scores. So that's really the only difference. We'll talk about using the table like this to get those different t-scores. There are some little issues about it we have to be careful of. And we'll talk about trying to have the calculator help us out tomorrow. But that's the big introduction. That's the big issue with 9.2 is having to use t-scores instead of z-scores.
This probably is a irrelevant question, but how come the T distribution is the area to the right of the tail?
It depends on how you express it. The
And
cumulative
in our table in
probability,
our book,
yeah, the cumulative probability, the
Yeah.
T, like this T is T 0.975.
right,
That's because that's the cumulative below that tail size of 0.025. And the tail size of 0.025 means the two tails together are the 0.05, which is the central 95%. And again, if you go to the bottom of that column, it's that 95% confidence level. It's just old-fashioned notation for it,
okay,
and it's frankly really irritating. And that's one of the reasons I've been trying to get us to think in terms of tail size, because I think that's probably the easiest reference for a T-scores. That's a really common reference. So single tail size is one of the common commands for T-score tools. So it's the one I'm going to try to get us to focus on a little bit.
so in our table in the book, all it has is the DF.
Yeah.
What's the
And
DF?
the DF, we'll talk about that DF more tomorrow, but I said that sample size of 100, right? So we
Yeah.
went here. Technically, this chart isn't sample size, it's degrees of freedom,
Oh.
which again is an old-fashioned tool. The degrees of freedom is the sample size minus 1.
Okay,
And we talked about it a little bit when we talked about finding standard deviation, why we divided by n minus 1. The degrees of freedom in the problem isn't the sample size. The degrees of freedom in the problem is 1 less than the sample size, because with everything but one of the samples values and the mean, you could calculate the others. It's a weird, complicated thing that is annoying that they keep doing the tables this way because of tradition and antiquity.
Okay.
But the degrees of freedom is 1 less than that sample size. So technically, for a sample size of 100, we should have been looking for degrees of freedom of 99. But 99 is not on the chart. What's the closest thing on the chart?
100.
100. So we used 100.
Okay.
Fair?
Yeah.
So we'll talk about that a little bit tomorrow. Again, a lot of things about T distribution tables are historic. They use these weird notations because they have used those weird notations for hundreds of years, and people who are comfortable with the tables are happy with it, so the tables don't change. It does make it a little bit irritating to learn to use these tables. But I often say for mathematics people, it's designed, all of mathematics and statistics is generally designed to be as easy as possible to use, not learn. And that does make a big difference. So it is unfortunate how T tables still look. But one could, I gotta let you guys go, but one could fairly, easily say, let's add a column for n. That's 2, 3, 4, 5, 6, 7, 8, 9, 10. And just add 1 to all those and have a column for n instead and use that. You could totally do that. So, well, why don't the charts do that? Because once you're used to it, you don't need it. Fair? Kim did not like that argument. She left. Ooh, it's past noon. I gotta let you guys go. So we'll talk more about that tomorrow, but that's that's where 9.2 is going. It's really that same tool. It is our approximation plus or minus the critical value times standard error. It's just that critical value, instead of being a z, is now a slightly larger t. That's the difference. Questions about that? All right, we'll play with that more tomorrow. Have a wonderful day. Anything you guys need before I send you off?
Nope. Thank you, Matt.
Okay. You're very welcome. See you guys tomorrow. Why is it-